Assalamualaikum Bu Nurul. Ya.
All right, very good afternoon to all participants, also to our beloved invited speaker. Assalamualaikum, selamat siang Ibu Amanda, Ibu Nurul.
Selamat siang.
Terima kasih banyak Ibu, thank you so much for your great availability to share with us here, especially with our participants who would join with us for our third seminar of World Class Professor Program. And today I'm really delighted to introduce Ibu Amanda, Septevani, as well as Ibu Nurul Widiastuti to our participants. So today we will have three invited speakers who will share variety topics related to the polymer and composites. We are still waiting for Prof. Pakorn. I guess he's still in the preparations to join with us.
I think he's here already.
Oh, is it
Yes,
already?
yes.
Oh yeah, he
Yeah,
already here. Yeah, finally I could find it. Maybe I can pin him to make it easier, as well as Amanda. And then right. And Ibu Amanda, if I'm not mistaken, now you are in Italy, right?
Yes, I am.
So how was Italy now?
Apparently I'm still in quarantine, so I haven't do anything yet. Yeah, but now it's about 8 a.m. in the morning.
8 a.m. Oh,
Yes.
just woke up, yeah? How was the weather there?
The weather is pretty cold, of course, compared to Indonesia. And I think mostly it's always a right rainy day.
I see.
But
Because
okay, the
it
weather.
turned to autumn, right? In Italy.
Yes, it's close to the winter very soon.
I see.
End of
Almost close to
September.
winter, yeah?
Yes.
And how many days you have to spend for quarantine in Italy?
It is 8 and 2 more days to go. So in total is 10 day. Yeah.
10 day. And you
Yes.
need to check again, yeah, to test again
Yes.
for the PCR.
Yes. There will be like a health person who come to our places and
I
take
see.
the PCR test for us.
I see. So
But
it's
I
quite
mean,
challenging, yeah, to
there is no
have.
symptoms, so it should be
I
okay.
see. I see. So means it's quite challenging nowadays to have a trip, yeah, during the pandemic.
Yeah, it is a very, I mean, challenging to have international travels. There's so many challenges and documentation that we have to complete it prior to our departure.
Yeah, I guess so. Anyhow, how many days you plan to stay in Italy for your
Yeah,
research
I will
activity?
be here until beginning of December. I mean, end of
Oh,
November
I
and
see.
back to the beginning of December.
And again, another quarantine, yeah, later on.
Yes, another 8 more days for quarantine.
Yeah.
But thanks to the online system, so even though we are in
Yeah.
quarantine, but we still have
Yeah.
a opportunity for doing some work.
Yeah, absolutely. Yeah, I
Yes.
couldn't agree more with you. This online platform really, how to say, provide us a great contribution, yeah, to make any
Yes.
kind of meeting discussions, yeah,
Yes,
real,
agree.
yeah,
Yes.
that's right. Hello, Prof. Pakorn. Very good afternoon. Yeah.
Good afternoon.
Yeah. How are you, Prof?
I'm good, thank you. I'll try to set up my two devices. Oh, sorry.
Oh, sure. Yeah, I guess you still need to adjust the audio. We got the reflections from the your audio, so hopefully it can be set immediately, ya. And Ibu Nurul, selamat siang Ibu. Assalamualaikum. Ibu, your audio still mute.
Waalaikumsalam. Selamat siang. Sudah kedengarkan?
Oh, sudah. Excellent, Ibu. Very clear.
Thank
Ibu
you very much.
Nurul, yeah, thank you so much also for your great availability to support our program. So I, as the, how to say, the person in charge for this program, really grateful to all of your great availability to support our program. And I've been reporting to the ministry that today we managed for the third seminar of podcast professor program, and we really, how to say, happy to introduce our three great speakers today. Yeah, hopefully we can learn again new things, yeah, from our invited speaker today. So for all of your information, as well for the participants who just joined with us in this seminar, this seminar is actually the third seminar of World Class Professor Program, yeah, organized by WCP program scheme B that fully granted by Kemendikbudristek Ministry of Education, Cultures, Research and Technology, and also strongly supported by LPDP. Yeah, this year is actually my fourth times for this program. So I've been involved for the World Class Professor Program since 2018. And yeah, up to 2021, very grateful. The government still give us, how to say, the great opportunity, yeah, to manage this. Hopefully next year we can extend the activities, yeah, together with Bu Manda, Bu Nurul, for the future topic. I really hope so. Since also Bu Manda will how to say, soon transfer, yeah, soon to be transferred to Bandung. Yeah, and with Bu Nurul as well, yeah, hopefully in the future we can find the new connections. All right, everyone, since now it's already 1 p.m., let me try to start this meeting on time. Usually 1 p.m. is quite challenging for our participants because it just fits for the prayer time as well as lunch. So yeah, sometimes it come a bit solid, but Even so, I guess let me try to start this meeting on time, and the participant maybe can join with us gradually. And let me try to start this meeting. Is it okay? All right. Okay, very good afternoon, everyone. Selamat siang. Assalamualaikum warahmatullahi wabarakatuh. Again, welcome back to all participants who really, how to say, loyal to join with our program since the first seminar. So today we are very delighted to introduce again our three invited speakers, yeah, who really, how to say, expert in their field, yeah. And today, similar to our first and second seminar, we still have Prof. Pakorn as the invited wood class professor program here. We will have three presentations from each invited speaker who will deliver, how to say, typical topics, yeah, that's still related with the polymer and composite science and technology. So as your preference, basically this seminar activity will be started by the presentation from each invited speaker for around 30 to 40 minutes, yeah, for each. And later on, we will move to the Q&A, yeah, question and answer. Of course, during the presentations of our invited speaker, I really, how to say, like to invite all participants to just write down your questions, comment, yeah, to each presentations. You don't need to wait until the Q&A session comes, yeah. So without any further ado, I guess let me start this seminar, yeah, the third seminar of Wood Class Professor Program 2021. And before we start the first presentations, yeah, here we would like again to welcome all invited speakers as well as our all beloved participants who already joined and also just joined with us. Welcome to Department of Chemistry Education, Indonesia University of Education, or in Bahasa, we well known as Universitas Pendidikan Indonesia. Or maybe Bu Amanda known, Universitas padahal IKIP ya, since we are come from the normal university. And then the committee could, I introduce again our invited speaker. Some of you who are also joined with us in our previous seminar, I do believe you already known with Prof. Pakorn, but since maybe some new participants who also joined with us today, so let I briefly introduce our first speaker. Yeah, the first speaker is Associate Professor Pakorn Opaprakasit. He currently in charge as a head Department of Common and Graduate Studies of Sweden International Institute of Technology, Thammasat University. He also been in charge as a director, yeah, in the Center of Excellence in Functional Advanced Material Engineering, or COE, yeah. And here is the following of his educational background. He obtained the bachelor degree from Chiang Mai University, Thailand, and then he obtained the master and also doctoral degree from Penn State University, United States of America, especially in the material science and engineering, particularly in polymer option major. And then I guess we still have other informations. Yeah, and here is the work experiences, yeah, of Prof. Pakorn. So if I read completely of his CV, is actually couldn't be finished within 2 minutes. Just I try to summary the important work experience that he been conducted, but currently from 2019, yeah, as we mentioned before, he is in charge as the head Department of Common and Graduate Science Studies of Sweden Institute, yeah, of Technology from Thammasat University, and also he he has the, how to say, important role, yeah, here as the fellow of Thai Academy of Science and Technology Foundations, and also he's still in charge as the executive board of Material Research Society of Thailand, or MRS, yeah, chapter Thailand. And also, again, as we mentioned before, he also in charge as the head of Center of Excellence in Material and Plasma Technology, Thammasat University. He been published 9 patents, yeah, and also many publications, yeah, in the Google Scholar or Scopus. It been recorded around 78 publications with the age index around 70. And then here is some of his current research work, yeah, that been conducted maybe so far up to now in his group, yeah, in his research group. So basically, if we follow his current research topic, is really related to the science and technology of the polymer and composite, yeah, not only regarding to the bio-based materials, yeah, but also some interesting composite system, yeah. In our first and second seminar, he been introduced some work, yeah, some recent work that related to his current work. And here is even is quite interesting, yeah, to know that he also working in the artificial intelligence, yeah, in the chemical detections and sensor. Very sounds interesting. If you are interested in to know more detail about his current research, you can easily attack the information on the Thammasat University website, as well as from his Google Scholar or Scopus. All right, I guess this the following information of our first speaker. And without any more ado, Prof. Pakorn, I would like to invite you to start your presentation. Time is yours.
Thank you very much, Professor Fitri, for your kind introductions. Also, good afternoon, the invited speakers, and also the audience who attend the seminar today. I think the majority of the audience we have met 2 times already from the previous 2 lectures. Now, for this lecture, please let me share my PowerPoint. So I modify the title of my talk a little bit for today. So instead of going through many techniques, many characterization techniques in that we use in polymers and composite characterizations, I will go and specifically to the technique vibrational spectroscopy and the applications. So from the outline, I will start from the basic concept of the technique, right? So vibrational spectroscopy actually focus on FTIR and also Raman spectroscopy, and how we use this in both qualitative and also quantitative analysis. And also I will give some example of the application of these techniques in research work in the field of polymers and also composite polymers. And as Professor Fitri already introduced, I work at the Center of Excellence in Functional Advanced Materials Engineering. So we deal with full circle of materials development, right? Starting from synthesis, right? Design, fabrication, and also applications. Now, let's go into the concept of vibrational spectroscopy. Right? So if everyone already know that spectroscopy technique, right, use light, right, or electromagnetic wave, right, and use them in applications and try to apply this to many applications. Depends on the wavelength of the electromagnetic wave. Right? We classify them into different regions with different names, right? And also, when we use them, we come up with different technique, right? Different spectroscopic technique. For example, in X-ray region, right, we have X-ray fluorescence spectroscopy. We have UV vis, right? And in the region of infrared, right, there are also near infrared spectroscopy, right? Mid infrared, and also Raman spectroscopy. Right. So my lecture today will focus more on FTIR in mid IR region, and also with some information in from Raman spectroscopy. Now, why, right? Vibrational spectroscopy? Vibration means vibration of bond, of a chemical bond, especially covalent bond. So if we imagine that we have atoms as balls and then connected to each other by a spring, and so this can vibrate, right? And the vibration here, right? We can calculate the frequency of the vibration, right, using this equation right here. So as a result, the frequency of the vibration depends on two parameters, K, right, and also the reduced mass right here. The K here corresponds to how strong the spring is, or in chemical bond, this is how strong the covalent bond is. And the reduced mass here depends on mass of the two atoms that are attached to each other. So as a result of this, right, different bond will vibrate at different frequency, right? So when this when bond vibrate, like they can also emit light and also absorb light that have the energy equal to the frequency of the vibration. So this brings us to the principle of the infrared spectroscopy, right? So what we need to do is we use light source, right, that generate infrared light for us, and then we shine the light through the sample. Right? Some of the light will be absorbed by the chemical bonds in the sample, right? And the remaining coming out, and we have a detector to detect how much light is remaining. Right? As a result, we can change this into the way that we can use, like, to interpret, get some information of chemical bond in the sample. So these are actually basic principle for any spectroscopy. And however, if we apply this to infrared spectroscopy, we will, right, get signals, right, only from vibration that have changed in dipole, right? So if bond, right, if chemical bond here and we have vibration, but during the vibration, there is no change in the dipole moment of the bond, right? So this cannot absorb infrared light, and we will not see signal of this type of vibration, right? Normally, if we have symmetry in the bond, so when they vibrate, so there will be no change in dipole moment. So therefore, we will not see signal from infrared spectroscopy of this type of bonds. However, right, if the bond have dipole moment now, and during the vibration, there is change in the dipole moment, now we will see signal in infrared spectroscopy. So as I already mentioned, so how fast, right? So the frequency of the vibrations depends on two parameters. The first one is bond strength, right? If we have stronger bond, the vibration will be higher at higher frequency. So as a result, if we have CC bond, right, triple bond will vibrate at higher frequency than double bond and single bond. Right? if we change the mass, right, bigger size atoms or smaller size atoms, right, when the mass decrease, the frequency will increase. Right? So therefore, we will see CH band, right, at higher frequency than CC or C chlorine or C to other atoms. But in molecule of any compound, there is not only one bond, right? Not only one chemical bond. There are more than one chemical bonds. Therefore, we will see many vibrations, right, occurring in the molecule of atoms, and these are all the possible vibration mode that can happen. Right? So we have stretching vibration, right? Symmetric or asymmetric vibration. We can also have what we call bending or deformation. Right? So this can also be divided further into in-plane bending, right? So scissoring, rocking, right? Out of plane bending, right? Whacking or twisting mode. Right? All of this, right, vibrate at different frequency depending on strength of the bond and also mass of the bond as well. Therefore, we will have many possibility of vibration or many possibility of infrared light absorption when we apply this to any sample. So those are infrared spectroscopy. Right? What about Raman? Right? Raman spectroscopy use different technique. So this technique use light with very high intensity or laser light, right, shining to the sample, and then it will generate scattering of light. Right? And if scattering is elastic, right, there is no change in the frequency. Right? But if inelastic scattering happen, right, for example, Stokes and anti-Stokes scattering here, we will see, right, different in the frequency of the light, right? So, and the difference in the frequency here, equal frequency in infrared region. Right? Therefore, as a result of this, we will see what we call Raman chip, which have signal in infrared region. And these are some example of setup for Raman spectrometer. Right? So we need to use high intensity laser, right, to shine to the sample, and then we get the signal, which are in the region of infrared light. And also we will look at Raman shift of or signal that we get from the sample. Now, there is also a selection rule, right, for Raman spectroscopy. We know that from infrared spectroscopy, we need to have a change in dipole during the vibration, right, to get signal from infrared, right, or FTIR. But to get signal from Raman, right, the vibration need to have change in polarizability or polarization of electrons. Right? For example, if we have bond between N here, when this vibrate, right, go in and out. So this will make the distribution of electron change or change in polarizability, right, of the bond. Therefore, this will generate signal in Raman spectroscopy. Right? If you still remember previously, this vibration do not change dipole. Therefore, we will not see signal of this vibration in infrared spectroscopy. Right? So as a result, these two techniques, right, FTIR, right, infrared spectroscopy and Raman spectroscopy, are complementary to each other. So we have complementary result from the two techniques. So we have various vibration in molecule of compound. If we have strong signal in Raman, the signal in if we have strong signal from infrared, right, the same signal in Raman will be weak, right? Weak signal in infrared, right, in Raman will be strong signal. So we can use these two techniques, right, to complement each other. So those are some basic concepts of the two techniques. Now, let's go further. Right? If we use only the previous setup of spectroscopy, we shine light through sample and then use detector to detect the light. Right? These are practical for other techniques that are not quite sensitive to the environment, like UV visible spectroscopy. Right? We can measure from one frequency to the whole range of the spectrum. Right? We can measure one by one, right? Point by point. However, if we do this in infrared spectroscopy, it will not yield us a very good result, right? Because infrared light can be absorbed by water in the air, right? Or some other gas in the air. So we will not have reliable spectrum. Right? Therefore, a technique that is called Fourier transform infrared spectroscopy, right, was invented. So by using this technique, right, we need to have a setup that have what we call a beam splitter that can split infrared light into two portions, right, go to reflect from a fixed mirror and a moving mirror. So by doing this, right, we can measure signal at different frequency at the same time, right? So we get all frequency, we measure all frequency, right, for the whole range at the same time and get the signal together, combined together. And so this is example. If we measure only 4 frequency, 10 frequency, and many more frequency together, right, we will have signal that look like this. This is called interferograms, right? So if we look at this, right, it has no meaning to us at this moment, right? But if we use a mathematical function like Fourier transform to apply to this signal that we have, right, we can convert this into a spectrum like this, right? So at the beginning we have interferograms, right, from the machine, and then using Fourier transform function, right, converting them into spectra, right? So we need to measure single beam spectra, right, only baseline, right, no sample, and then our sample. After that, if we ratio between these two spectra together, we have the final result of infrared spectrum. So this can be either in the form of transmission. So this detect, right, the remaining light that come out, right? So transmission, or we can convert this into absorbance. Right? Doesn't matter. We can convert back and forth between them, right? Depends on who are familiar with which mode. Right? So, but if you want to do quantitative analysis, right, normally absorbance mode is more practical. All right. So from this technique, right, we can have signal that correspond to like stretching mode or bending or deformation modes. Normally, stretching band have occur at higher frequency than bending band. Right? And also another interesting mode is called overtone or combination mode. Right? Overtone or combination mode here. Imagine that you play piano, right? You have do note right here. You have the other do note at higher frequency. Right? That is the concept of overtone. So if you have fundamental mode right here, right, you multiply the frequency by 2, you may have overtone combination mode right here, right? And also this is 2 times or this is 3 times. So you have overtone mode, right? But the intensity of the overtone mode may be weaker than the fundamental modes, right? But sometimes they're important, and I will show some example later on. Right. So these are another example of overtone and combination. Right? If you have a band at 3600 and a band at 1600, if you combine this together, you may have a combination mode at around 5200 wave number as well. Right? So sometimes these are in the region of near infrared. Right? So we also can apply this into NIR or near infrared spectroscopy as well. Right? But some overtone combination may appear in mid-infrared spectroscopy as well. And this technique is actually very versatile and can be applied in characterization of various type of materials, right? Especially if you have all the required accessory that you can equip with your instrument. You can measure any type of materials and have important information, right, from this technique. Not only just identify you have this peak, and then you have what type of bond, something like that. That is very basic information, but we can get much more detailed information from this technique. Now, when we have different type of accessory, right, we can measure, right, we can measure infrared spectrum in various modes, right? These are 4 important modes. The first one is transmission, right? We just shine infrared light through the sample, right? So this is called transmission mode, right? If we use, right, crystal that can reflect infrared light inside the crystal, so this is called ATR, or attenuated total reflectance mode, right? Which is very, very convenient, right? And another mode, if you have sample that have very dark color, like coal or graphene materials, right? Something like this, you may want to use the technique that is called diffuse reflectance mode or drift mode. Right? Or if you have a very, very thin layer of material in nano scale, for example, coating on surface of other materials, you can use like specular reflectance mode, right? So these are 4 important measurement of infrared spectroscopy or FTIR spectroscopy. We may use more of the first 2, transmission and ATR, right, in normal measurement. So now, for transmission mode, we also can measure sample in solid, in liquid, or in gas mode. Right? We can apply this in qualitative or quantitative mode, right? And by using different type of accessory, right? And also by combining our sample, right, or dilute our sample with compound that do not absorb infrared light, right? The most common one is potassium bromide or KBr. Right? This compound will not absorb infrared light, so we can use them to dilute our sample. Right? In order for, right, get high quality spectrum, especially if we want to do quantitative analysis, right? We need to have high quality spectra that follow what we call the Beer-Lambert's law, right? A equal absorptivity times path length and times concentrations. Right? So these are examples. If you want to measure, right, if you want to measure a sample in gas form, right, you need to use a gas cell, right? And because gas has very low concentrations, right, you need to increase the path length in order to increase the intensity. Right? The path length means you need to make sample go through your sample. Your sample should be very thick, right? Therefore, in this gas cell, there are mirrors that light can go back and forth many times to increase the path length. For example, this, even though this is only centimeter, but the whole path length can go to 2 meters, right, or 10 meters for this cell, for example. And these are spectra, example of spectra that we get from gas sample. We can also make a sample, right, by mixing with KBr powder and make them into pellet, right? Compress them into pellet and then measure the measurement, the spectrum. We can make them into standalone film, right? But they need to be very thin. Right? If you have thick film, your signal may not be as of high quality, suitable for especially quantitative analysis. Right? We also have like liquid cell. Right? You can put your sample in liquid form into the cell and then measure spectra in transmission mode. Right? So these are all a possibility that we can have in order to measure sample in transmission mode. Okay. So again, the sample just go, the infrared light just go through the sample and we detect the remaining or the transmitted beam, right? And we get the signal. Right? So in order to have high quality spectrum, right, we need to make our sample distribute equally, like homogeneously in the metric that we use. Doesn't matter, you use gas cell, you use liquid cell, or you use accessory for solid materials. Now go to the second mode of measurement, right? ATR. In ATR mode, right, we utilize the property of light that can reflect when light pass through medium that have different refractive index. So if light pass through material with high refractive index to low refractive index, right, normally it will reflect all of them, right? But small amount of light can still penetrate to the other region, right, of the medium. Right? So we call this evanescence wave, right, which is very important. So this wave will give us the signal in ATR measurement. So we need an accessory that is called ATR accessory. Right? Normally consists of a crystal, and this crystal can be made from various type of materials that is transparent, right, to infrared light, right, does not absorb infrared light, and each one of them will have different refractive index. And then we just put the sample right here and we apply pressure to place the sample, right, in contact with the crystal. After that, we just shine infrared light, right, generate evanescence wave right here that can give us the signal. Right. Now, the unique character of this technique is the depth of penetration, right, into the sample here depends on many factors. Number one, depends on the refractive index of the sample, refractive index of the crystal, right? Number two, right, depending on frequency or wavelength of the infrared light, and also depends on angle of refraction of the beam, right? So there are three variables we can vary, right? And this also offer opportunity, right, to play or to get more important information or detailed information from the measurement. I will go to that later on, the detail. Another mode is diffuse reflectance, right, or drift mode. So from this mode, right, these are usually suitable from sample with dark color, right, that can absorb so much of the infrared light. Right? So we can now mix the sample with KBr to dilute the concentration, right? And then we just shine light to the sample, and then we measure the diffuse reflectance signal. So, and these are example of spectra of the same material, measure from different technique, right? The top one is ATR, right? The bottom one is transmission. The middle one is from transmission, and the bottom one is from drift technique. And you can see, even though these come from the same sample, right? The relative intensity here are slightly different, right? This is because of the different nature of the measurement, right? However, we can convert each one of them to be a uniform pattern, right? By using a software, right, to correct, right? We call advanced correction function, right? We can convert ATR spectrum into transmission spectrum. We can convert drift spectrum into transmission spectrum for comparison as well. Now, if you look at ATR again and look at this equation, this is the depth of penetration of the wave, right? Normally, we will get signal from the surface and then go, right, deep into the sample, right? Depend how deep, depending on this equation, right? Depend on three factors that I already tell: refractive index of the crystal, wavelength, and also angle of the beam. So we therefore can make an accessory that we can vary the angle of the beam, right? So we can vary the angle of the beam in order to control how deep we want to detect, right, our sample. Right? If we want to detect only the surface, right, we make the angle here, right, very wide. Right? If we make the angle narrower and narrower, right, the beam can penetrate deeper and deeper into the sample. Right? We can have the information that is called depth profiling information. And these are some examples of crystal that are employed to make ATR accessory. Right? And each one of them has different refractive index. Therefore, each one of them, right, will provide us different depth of penetration into the sample. If we use the same, right, the same type of crystal, right, and we use different angle, right, you can see zinc selenide here, right, at 45 degrees, right, the depth of penetration is higher than at 60 degrees. So these two lines, right, come from the same crystal, right? So we go deeper, right, into around 2 micron for zinc selenide at 45 degrees, right? Only 1.1 micron at 60 degrees. Right? But also you can see same setting, right? We will see depth, higher depth at lower frequency and lower depth at higher frequency. Right? So we cannot change anything from this, right? Because this is the nature of the light. So as a result, if you compare, if you have spectrum from ATR, right, you compare with similar spectrum from transmission, you can see the ATR spectrum, right, is stronger at lower frequency region. Right? This is stronger than this one. Right? But if we go to higher frequency region, right, the ATR spectrum will have weaker intensity compared to that from transmission mode. Right? So this is the difference, right, between the result that we get. But as I already said, we have mathematical function that we can convert them to be comparable, right, by using a program. Now, we can also have different type of accessory, right? ATR accessory to do different type of measurement. If our sample is very diluted, if our accessory can have only one refraction, the signal will be very weak, right? But we can make ATR crystal that can have many refraction, right? So when there are many refraction here, we also will have stronger and stronger signal, right? So this is also another type of accessory that we can find. And also more advanced technique now, we can make ATR, right, crystal into a form of fiber optic probe, right, that can be used at high pressure and high temperature. So as a result of this, right, we can stick the probe, right, into our chemical reaction. For example, if you do chemical reaction at very high temperature, at very high pressure, you just put the probe in here, and you can measure the spectrum of the solution or your reaction real time, right, as a function of time. And you can, when you have the result, you have many opportunity to play with your result and get important information. And recently, and very even more advanced technique, right, are available from Ford Thermal company. They can combine, right, the measurements of both Raman and infrared light at the same time, right? So you have only one machine, right? You measure one spot, right? You get both signal of infrared and Raman, right, from the same spot. And you know from the beginning that these two techniques are complement to each other. So you have all the information that you want, right, from the same spot of measurement. And also, this technique can enhance the resolution of infrared measurement as well. You can go to very small spot into almost nanometer region, right? So these are very promising technique, right, for future work in material characterizations. So these are some the basic information about vibrational spectroscopy, right? Now I'll give you some example of the information that we get, right, from applying this, apart from only look at what peak we have, right? So we can have more information, right, deeper information than that. This is one example, right? We can look at free and hydrogen bonded OH group and then try to determine the structural conformation from the sample. Right? So if you look at this sample, this cyclic compound are called calix-arene that have OH group. Right? This OH group can form hydrogen bonding with each other. So if OH group, right, is free, do not form hydrogen bonding, the bond here is quite strong. So we will see peak at high frequency, right? Normally around 3,500. Right? But if OH group form hydrogen bond with other groups, this bond become weaker, right? Therefore, we see a shift in the peak, right, to lower frequency, right? Hydrogen bonded OH group. So from this result, like these three spectrum, right, therefore we can identify the strength of the hydrogen bonding. Right? If it go to very low frequency, the strength of the hydrogen bonding is very strong. Right? The OH bond become very weak. Right? So signal happen at lower frequency. We can also study hydrogen bonding as a function of temperature, right, by using accessory that we call heating cell. Right? We can put sample in here. We can control the temperature, right? from room temperature until 200 or 300 degrees Celsius and measure the spectrum as a function of time, right? And we can see nature of hydrogen bonding. And from this result, we can tell, right, what type of structural information we have in the sample, right, as a function of temperature. We can also apply this to measure what we call inter and intramolecular hydrogen bonding, right? So this work is used to study structure of phenolic resin. Phenolic resin have OH group, right, quite similar to Calyx arene before, right? But this is long chain linear polymer, right? So we can use this technique to determine the strength of intramolecular hydrogen bonding inside the chain, or hydrogen bonding between different chains, right, that have different strength, right, also show peak at different intensity, right? So right here, the peak right here is free hydrogen bonding, right? And when it shifts to lower frequency, right, so the strength of hydrogen bonding becomes stronger and stronger. Normally, the shift is around 100 to 300 wave number for OH group. Okay. We also can look at the peak of carbonyl group, right? For example, this carbonyl group are usually located at 1700 something. So free carbonyl group, right, with no hydrogen bonding, right, are usually around at 1760, right, wave number. Right? This is free hydrogen bonding. But when we mix OH group, right, this OH group can form hydrogen bond with the carbonyl. It makes the shift, the band shift to lower frequency the same way, right? But the shift is around only 20 to 25 wave number, right? This is common for carbonyl group, right? So as a result, we can look at, right, the intensity of this peak and this peak, right, to tell how much free carbonyl, how much hydrogen bonded carbonyl we have in the system, right? How much, right? We can use what we call curve or peak resolve technique, right, to get band area, right? So actually, this is OH stretching mode. Right? You see very broad spectrum like this, right? It consists of so many peaks in here, right? So we can use a curve fitting technique, right, to determine how many band or how many peaks we have, right? So as a result from that, we can also study the nature of hydrogen bonding, right? So this is very unique study that I want to show with everyone. So this is a measurement of solution, right? Solution of this compound, right? This compound has OH group, right? So if we mix this with non-polar solvent like cyclohexane, so this will separate this compound from each other, right? If the concentration is very low, right, very low, we may be able to see this, right, completely separate from others, right, meaning that no hydrogen bond, right? So we can see peak of free hydrogen bond OH, right, free OH stretching. So these are two spectrum, right? This is the solution. This is only solvent. If you look through these two spectrum, right, you may not detect any much difference between them, right? But if you look closer, this is the difference that we can see, right? This feature right here is the difference. Now, if we make subtraction, we use A, right, minus B. We have a different spectrum like this. And you can see other patterns that are the same, right, will go to the baseline. And we have only the peak of our sample, right? So this is free, right, peak of free OH group. right? No hydrogen bond. But if we increase the concentration, right, they come closer to each other, they can form hydrogen bond. We start to see peak in this area, right? So this is dimer, trimer, multimer. Dimer means 2 molecules, right? Trimer means 3 and 4, and so on. So if we have this information, right, we can look at the nature of hydrogen bonding in the system, right, by using curve fitting and proposed equation here for hydrogen bonding. I will not go into the detail here. And also we can, if we apply, right, 2 type of molecule together in the solution, this is the spectrum that we can get. Right? Again, we have free OH peak right here, and then hydrogen bonded peak in this region. So those are information on very basic or concept of hydrogen bonding in polymer. We can also use this to study crystal structure of materials. Right? For example, here, polylactide, that if we have polylactide, right, single component, they have structure that is called homocrystalline structure. If we mix 2 types of polylactide together, they generate a new type of structure that is called stereocomplex, which is different from homocrystal. Right? So we can use infrared spectroscopy to study this, the difference in the 2 nature of this crystal. And this is also quite unique. These are 2 spectra that come from the same materials, right? But the top one here come from freestanding film, like making film, and the second one here come from solution cast film, like on KBR window. Right? The bottom one here, sample is very thin. Right? When sample is very thin, you can see the spectrum is very good, like high quality, suitable for quantitative analysis. But there are some peak that is quite small, right? This region, that can give important information, right? So if you look at this region, the peak is very small. Right? If you want to have information from this region, what should you do? Right? You can increase the thickness of your sample, right, to get this peak bigger, right? But when you do that, you sacrifice, right? Some big peak here will be overabsorbed. That is not suitable for use anymore, right? However, you get information from small peak, right? So you can use these 2 spectrum to get the full set of information that you want, right? And also, if you look right here that I mentioned, this area are also the area for overtone combination mode as well, right? So the overtone combination mode here can be very weak, right? If you want to get information, we need to have thick sample. So this become bigger peak, right? Actually, this is similar to this peak. Right? This is overtone of carbonyl group. Carbonyl group is at 1700 something, and this is 2 times, which is around 3400 something, right? So we can get the same information either from here or from here. So if we look here, the information from 3500 and 1700, they show the same behavior, right? So these are some strategy that we can play with to get information, like from infrared spectroscopy. We can use this to identify trace component in materials. Right? For example, if you have additive or plasticizer in very small amount in your sample, you can use infrared spectroscopy to identify them. Right? But you need to normalize peak that does not have different characteristic, right, to make them have the same intensity and find different feature in other region. Right? Try to identify information you can use ATR accessory, right, that have different number of refraction, right? So higher number of refraction will give you stronger signal, right? And this can be applied for quantitative analysis. Right? You can also use transmission mode, right, in quantitative analysis as well. This result show us a formation of lactide, right, from degradation of PLA. Right? We see this peak right here, right, that change with the condition of our reaction. So if we want to quantitatively determine how much, right, we can prepare standard sample, right, standard sample, and then measure intensity of the characteristic peak, and then make a standard curve. Right? After having standard curve, now we can determine the amount of lactide in our sample. Right? So these are the results. We can measure surface characterization, characteristic of materials. Right? In this work, we make medical growth from rubber, and then we embed nanoparticles that contain antibiotic drug, right? And embed that on the surface of the growth, right? And we can use infrared spectroscopy to detect how much or how deep they are embedded on the surface and into the matrix of the growth. And also we can detect reactions, right, at the surface as well by using ATR. Right? So by studying depth profiling, right? Depth profiling, right? If you still remember, we use this equation again, and we can change angle of the beam in order to make the beam penetrate deeper and deeper into our sample. Right? We can see only feature on the surface, or we want to look more into the matrix of the material. These are also possible. And here, I think I'm maybe running out of time here. I'll show one or more example here. This is the study of structure and interaction in structure of coal. Right? Normally, coal, right, have a cross-link point that are made from covalent bond, right? But in some coal that we call low rank coal, they have what we call physical cross-link, right? That have a negative charge functional group, right? That bind with metal, and this is similar to ionomer structure, right? So we prove this, right, by treating the coal with acid group. So when we treat coal with acid, it converts carboxylate here into carboxylic acid group. And then we take spectrum of the original coal and the one after treated with acid, right? And look at the different spectrum. Right? The negative peak here tell us what functional group that are converted as a result of the treatment. Right? The positive peak show us what functional group that are generated, right, because of the treatment. Right? So this can be used to explain our mechanism. All right, so I think because of the time limitation, actually I prepare another part that focus on 2D correlation spectroscopy. Maybe I will save this for the future lecture, right? And I will stop my presentation here. Right? I hope that I'll give you some background information, right, about the vibrational spectroscopic technique, right, especially FTIR and Raman spectroscopy, and some example of application of this technique that can give us a deep detail, right, in the structure of materials, especially polymers and composite materials. All right, thank you very much.
Thank you very much, Prof. Pakorn, for your systematic and comprehensive talk. Yeah, it's really wonderful. From his presentation, we just realized that this vibrational spectroscopy technique was so powerful, yeah, Prof. It can help us, yeah, to characterize and to how to say to obtain more information, not only about the structural confirmations or interactions in the polymer blend, yeah, even though the crystal structures and also how to say surface characterizations and so on. And the good thing is Prof. Pakorn also provide how to say many great strategies, yeah, how to do quantifications based on the FTIR spectra. I do believe most of the audience or participants have a great experience with the FTIR spectra. So later on discussions, they can have the great interactions with you, yeah, to deliver the questions.
Yes.
All right, thank you again, Prof. Pakorn. And now we would like to move to the second guest speaker. We have Ibu Nurul Widiastuti. So before he start his her presentations, here again I would like to introduce briefly our second speaker, Ibu Nurul Widiastuti, Ph.D. She is a chemistry lecturer of Institut Teknologi Sepuluh November or ITS Surabaya. Yeah, I'm not sure, Prof. Pakorn, have you been to Surabaya? It's
No,
located in the East Java. Never been, yeah?
no, never been there.
Yeah.
I wish in the future I will.
Yeah,
Sure.
hopefully, yeah. That's one of the greatest place, yeah, in
Uh-huh.
Indonesia, I guess, with very excellent food in Surabaya. And Ibu Nurul also in charge as Vice Rector of Academic of Institut Teknologi Kalimantan. Yeah, and here is her following educational background. Yeah, she obtained the bachelor degree from Institut Teknologi Sepuluh November, ITS, and then she obtained the master degree from Institut Teknologi Bandung in the major of physical chemistry, and for the PhD program, she obtained the PhD degree from Curtin University of Technology, Australia. And next. All right, here is her following professional experiences. Yeah, she has been, how to say, conducted the main role as a chemistry lecturer in ITS from 1995 to now, so very senior lecturer, I guess. Nurul with the great experiences, and also she has the great, how to say, activities in the research and development coordinator of Center for Educational Development and Instructional Activities of ITS. He also in charge as the head of Center for Curriculum Assessment and Development of ITS. And also, as mentioned before, she is also the vice rector of Academy of Institut Teknologi Kalimantan. It's more than great to have you here, Bu Nurul. You are really the important person, yeah, with a really, how to say, yeah, important role, yeah, in the university. And from the Google Scholar and also Scopus, it's been recorded. He has around 40 publications with the domain, and very, how to say, pleased to inform to all participants. He also has received some awards, yeah, especially here it mentions award about Louis Satya Madhya from Rector of ITS, and also Best Presentation Award in the 6th International Conference on Engineering and Innovations Material in Tokyo, and also John Brody Medal from Australia Engineer for Best Paper in Chimica in Melbourne on 2007. And next, yeah, here are some research experiences of Ibu Nurul. Yeah, if we how to say summary from her research experiences, so mostly she has been working on the membrane development, I guess, yeah, based on the polymer and also polymer composite system, yeah. Here, development of metric membrane based on zeolite template carbon for gas separation, and also he developed the anhydrous film from highly supernative, yeah, incorporated with mold, yeah, in certain conditions, and also, yeah, he even improved the composite membrane system based on Thammasat and family, yeah, with some how to say material, yeah, for the fuel cell application. We have some similar interests, Bu Nurul. Hopefully in the future, yeah, we can start
Okay.
to make a collaboration
Sure.
in development of polymer composite. All right, Bu Nurul, without any further ado, I would like to give the time you start the presentation. Please.
Thank you very much, Dr. Fitri, for kind introductions. And very good afternoon, everyone. Assalamualaikum warahmatullahi wabarakatuh. First of all, I would like to thanks to the committee of the world-class professor from Department of Chemistry Education, Indonesia University of Education for inviting me in this event. And very good afternoon, Professor Pakorn from Thammasat University. And you already present the interesting presentation for that, and hopefully we can collaborate for our research in the future. And we would like to invite you to come to Institut Teknologi Surabaya, ITS, hopefully. And very good morning, Dr. Amanda. He is in Italy and still morning at the moment. And today I would like to talk on the mixed matrix membranes. Mixed matrix membranes, especially with the inorganic filler for gas separation and water treatment. And allow me to share the presentation. She already.
Yep. Excellent. Yeah.
Okay, thank you.
Slideshow, I guess. Yeah.
All right. Okay. Okay. All right. So today I would like to talk on the polymeric membranes with inorganic filler for gas separation and water treatment. And I'm from Chemistry Department, Faculty of Science and Data Analytics, Institut Teknologi, Surabaya. And as we know that membrane is a selective barrier that allows the passage of a certain constituent and retain other constituent, as we see in this figure. The membranes can be found in different type of modules, such as hollow fiber membranes, spiral wound membranes, tubular membranes, and flat sheet membranes. All of this can be prepared by using the polymeric as a membrane matrix. Then the next one is about the types of the membranes. We can use normally three kinds of materials called polymeric membranes, and then the inorganic membranes as well. And each of them have advantages and disadvantages. For example, for polymeric membranes, they have advantages such as desirable mechanical strength and compact geometry, low cost, uncomplicated manufacturing, and predominant commercial at this time. However, these polymeric membranes have disadvantages such as low separation performance in special case, and structurally weak and temperature limited, and also relatively short life. On the other hand, we also found inorganic membrane with advantages such as high thermal and chemical stability and superior separation properties. However, the inorganic membranes have disadvantages such as high cost, easily brittle, and complex manufacturing processes. And because of these advantages and advantages of both material, now is increasingly developed mixed matrix membrane, where the membrane is combined between the polymeric membranes and inorganic membrane used as a filler here. And before that, I would like to present here on how we prepare the membranes. First is we prepare the solution casting by mix the polymer with the solvent, so we can make the solution casting. And also for preparing the mixed matrix membranes, we can use inorganic fillers such as zeolite, MOF, ZTC, metal oxide, and etc. After preparing the solution casting, then we can cast using the rod or plate. It depends on the module that we would like to prepare, and then we can evaporate to dryness if we choose this method without immersing in a coagulation path. And also, if we prefer to use the non-solvent induced phase inversion methods, then this polymer solution can be immersed in the water coagulation path. Then we can create the membranes. And here is the examples of flat sheet membranes. Flat sheet membrane, as we can see here in this figure here, there are different type of flat sheet modules. Flat sheet modules like this, and we can use this in many kind of application. Another module is a spiral wound. Spiral wound, we can see here the feed solution that we will aspirate it goes through this side, and then the membrane will aspirate the feed solutions, where the selected constituent will come to the inside the pipe after goes through the membrane and will come out as a permeate here. And another constituent from feed solution will come through the concentrate side here. And different kind of modules membranes is called hollow fiber membranes. Hollow fiber membranes has diameter less than 0.5 millimeters, and there are two kind of these membranes called capillary membranes, with diameter a bit bigger than the hollow fiber membranes, which is 0.5 until 5 millimeters. And this is how to prepare the hollow fiber membranes or capillary membranes using the polymer solution, as I mentioned before, and then the polymer solution goes through the spinneret at a certain size that we can set based on the diameter of the membrane. So after that, the membranes comes to the coagulation path and then flushing path, and we can roll the hollow fiber membranes after that. And this is how the membranes modules work. So the process of feed flows come here inside the hole or the diameter of the hollow fiber, and then the feed will goes through the membranes, and we can found the permeate here, and another one is called retentat. And the last one is tubular membranes. Tubular membranes, we can apply pressures here to a reservoir filled with a polymer solution. Here is a polymer solution. So that the solution falls through the hollow pipe, and at the end of the pipe is a casting pop. This is a casting pop with small holes which the polymer solution is forced. So the porous tube is moving vertically, and a film is cast upon its inner wall. So the pipe here then immersed in a coagulation path where precipitation of the cast polymer solution lead to the formation of tubular membranes, same as the other type of modules. And next one, I would like to talk more on the application of mixed matrix membranes that we have conducted at the moment. So first is gas separations. Here is the membrane technology for gas separation. As we see here, the part of the membranes in industry, they work for the gas like this. And the important things for gas transport mechanism through membranes is the mechanism called Knudsen diffusion, molecular sieving, and also solution diffusion. For Knudsen diffusion, the mechanism of the separation of the gas is based on the rate of diffusion of the gas molecules. So the gas molecules will go through the pore size of the membranes with the rules of zigzag like this. And based on the diffusion rate, so the gas will be separated by the membranes. And the next one is molecular sieving. In molecular sieving, the key of the selectivity of the membranes is really based on the size of the pores of the membranes, or the material that we use for the membranes. And the pores of the membranes is a key, and based on the size of the gas molecules that will be separated. So if we want to separate the gas, so we can design the pore size of the membranes based on the size of the gas. So the smaller size of the molecule gas compared to the pore size of the membranes will go through the membrane, while the gas with bigger molecular size will rejected on the surface of the membranes. And the last one is a solution diffusion. In the solution diffusion, there is no pore size of the membranes, but they call the dense membranes, and the gas transport mechanism is based on the solubility differences between the gas and the interaction with the gas and the polymer materials that we use as membranes. So the challenge in gas separations is really based on the demand and the technology. They need to improve both the permeability and selectivity. However, both parameter is normally opposite. When we increase the permeability, so the selectivity will go down. So the challenge is how to keep the permeability and the selectivity still high. And in the gas separations, we also have a standard called Robertson upper bound. As we see here, the Robertson upper bound for organic polymers, that's a bit lower than the trade-off curve, while the inorganic membranes, that's higher than the trade-off curve. And with combining both of the materials called mixed matrix membranes, they will improve the performance of the organic membrane in order to achieve the trade-off curve of Robertson upper bound here. So the challenge in mixed matrix membranes is really depend on the polymer matrix itself, and also the filler that we will use for the mixed matrix membrane preparations. And in our research, we propose the quite new kind of materials called zeolite templated carbon. So the zeolite templated carbon is synthesized from the zeolite as a template, and we use a carbon source such as sucrose or other materials like furfuryl alcohol, etc. as a carbon source, or sugar that can be possible used as a carbon source. And the carbon source will was impregnated inside the pore size of the zeolite, and then followed by the pyrolysis at high temperatures, normally above the 800 degrees Celsius, and then we can find the zeolite carbon composite. And after that, we break down the structure of the zeolite using exit treatment to produce the zeolite templated carbon, which has called negatively structures of the zeolite. So in our research, the zeolite templated carbon and also the zeolite carbon composite was used as a filler for improvement the compatibility, permeability, and selectivity for mixed matrix membranes. So here is the advantages of using zeolite templated carbon to improve the permeability and selectivity, and also to improve the compatibility, because the materials have higher surface area as compared to other activated carbon, and also has a smaller pore size as compared to other activated carbon. And what the challenge is a mixed matrix membrane when we preparing the materials. In general, the mixed matrix membranes has a specific problem called the void that produce at the interface of the filler, inorganic filler, with the polymeric matrix. So the void can reduce the selectivity and also in general reduce the performance of the membranes. So that's why we are trying to improve the performance of the mixed matrix membranes with different kind of methods called annealing and coating, and also we combine the annealing and coating. So hopefully we hope that these methods will improve in order to decrease the void at the interface between the inorganic filler and also the polymeric phase. So it will reduce the void and also will improve the selectivity of the membrane itself. So here is the research motivation and the contribution of the research. We propose the new material fillers called zeolite templated carbon, and after that we use that as a filler in the mixed matrix membranes with polymer matrix of polysulfone. Then we modify the membranes with the surface coating and also with the heating above the polysulfone gas transition temperatures. So here's the illustrations of the modification of post-treatment hollow fiber polysulfone ZTC mixed matrix membranes. And this is the methodology of this research. In general, we prepare the polymer solutions, yes, and we use the module called hollow fiber. We use the hollow fiber membranes with a certain condition for the preparations, and also we followed the treatment on the surface coating and heating treatment. And after that, the membranes was tested using the gas separation test for single gas and also for mixed gas tests. And here is the result for the synthesis of the ZTC. We can see here the surface area of the ZTC is much higher than the composite one and the zeolite as well as a template in this case. And also the pore volume here for the ZTC is 0.95 cc per grams, and the average pore size is much higher from the ZTC compared to the composite and the zeolite. And this is the result from the TM analysis, where show the micropores, and also we can find the mesopores as well in the materials. So the benefit of these pore structures, the micropore will contribute to the selectivity improvement, while the mesopores will contribute to the permeability improvement. And we also try to test the ability of the zeolite templated carbon as a CO2 absorbent, before we use as a filler in mixed matrix membranes. And based on these results, the materials can absorb the CO2 and also possibly release the CO2, because the interaction between CO2 and the zeolite templated carbon is only physically interactions in this absorption. So then we continue to use the ZTC as a filler for mixed matrix membranes here. As we saw in this fig, the mixed matrix membranes of polysulfone and ZTC gas separation performance with variation in heating temperatures, also the coating concentration and its combination for gas pairs, which is CO2 and methane, and also hydrogen and methane, compared to the Robinson curve and other studies. As we see here, in gas pairs of hydrogen and methane selectivity, we found that some of the membranes already achieved the permeability and selectivity based on the Robinson curve above the curve over here. It means that the achievement of the membrane's performance for gas separation is a potentially used, especially for hydrogen and methane separations. And this is the permeation and selectivity of gas pairs of CO2 and methanes, and also hydrogen and methanes on the mixed matrix membrane polysulfone and ZTC at 190 degrees Celsius with variation in thymos concentration. Thymos is a tetramethyl orthosilicate that we use as a coating agent for the membranes. And here's the illustration of the prediction of gas diffusion mechanism. For the annealing process, the key important part of the membranes is the surface area of the membranes, which is possibly gas transfer through here using the solution diffusion mechanism, where the coating process is a solution diffusion on the top of the membrane with the dense layer over here. When we combine both of the modification, we can find the solution diffusion on the top of the membranes with the dense layers, and also the surface membranes like we found in the annealing process. To avoid or reduce the void of the membranes based on the interface between the polymers and also the fillers itself. And this is the SEM results showing that at certain conditions we see that the void from the interface between the polymer matrix and the fillers is already reduced compared to before the modification. And this is the result for the topography using AFM, and we can see at the annealed at 190 degrees Celsius and coated by thymos at 0.03 moles, the surface of the membranes get smoother compared to other membranes at various treatment here. And this is the TGA curve of mixed matrix membranes before and after annealing process. As we see here, the effect of annealing is can make the thermal stability enhancements due to the higher additions. And at the moment we try to conduct it. We are conducting the research using those kind of materials. Some of them, as I presented here, and we apply this kind of materials in CO2 separation from biogas palm oil mill effluents called Polymer. Yes, and normally in this industry, in this palm oil industry, they use a pond here, and with anaerobic process to produce the biogas. However, the biogas here is contain high amount of CO2. Yeah, high amount of CO2. So the CO2 content should be reduced. Yeah, should be reduced to improve the color of biogas. Thus, the CO2 of the biogas need to be separated. So we conducted research to reduce the CO2, the percentage of CO2 in the biogas, to improve the performance of the biogas. And the next one is a polymeric composite membranes for apple juice purifications. Yeah, this is the we in our daily life we often drink apple juice, and one of the process for producing apple juice is using the membranes. Yeah, using the membranes in order to clarify the apple juice, because the apple juice contain the colloid that caused by the browning reaction from the enzyme. So we try to separate, yeah, the particle of the browning to produce the clear apple juice here. And as we can see, the result of the apple juice clarifications with PVDF and cellulosic acid membranes from cloudy to clear here. And this is the permeate flux of the apple juice. And this is the characterization of the membranes from cross-link and surface morphology using the SEM and also the topography by AFM of the PVDF-CA membranes with polyethylene glycols at the various concentrations. And we can see here the effect of polyethylene glycol here at the lower concentrations. They can control the pore size of the membranes to make homogeneous and smooth over here. However, we increasing PEG up to 5%, so the polyethylene glycol affect on the pores of the membranes that make much bigger pore size over here. So we decide to choose the maximum amount of polyethylene glycol, which is 3%. And this is the comparison of the morphology of membrane structures before and after, and also the topography of PVDF-CA membranes with 1% of PEG addition before and after also. As we can see here, before and after of the clarification process, we see the block of the membranes on the surface of the membranes itself. So these membranes need to be cleaned or washed. Yeah. And this is the infrared spectra of the PVDF-CA before and after. As we can see, the different peak here showing that this is because of the functional group from the reaction of the fruit browning due to the enzyme reaction. And the next one is PVDF lithium chloride polymeric membrane for harvesting of nanochloropsis as a microalgae. The motivation of this research is we tried to conducted research on producing bioethanols from microalgae. The state of bioethanol productions is first is pretreatment, fermentation, distillation, and purifications. Now, in order to use the microalgae, the first stage of this part is how to harvest the microalgae. Before we proceed to the fermentation process and in order to produce the bioethanols. And that's why in our previous research here, we tried to use membranes for microalgae harvesting. But the challenge of these membranes for microalgae harvesting is the block or the fault. The fault of membranes on the surface of the membranes. Well, we use that for rejected the microalgae. That's why we are conducted a research on how to wash the membranes after using for harvesting of nanochloropsis. And this is the illustrations why we tried to use lithium chloride here as polymeric membranes. As we see in this illustration here, the lithium chloride did not chemically bind to the PVDF polymers, but the presence of lithium chloride result in a change in the structures of the polymer chains phase alpha to beta phase on the PVDF membranes. Then the lithium chloride will dissociate into ion lithium and ion chloride. The lithium ion as a cation will have ion dipoles interaction with the carbonyl groups in NMP as a solvent. So the lithium chloride can be completely dissolved with the NMP solvent. It can cause a high increase in viscosity of the dot solution due to the interaction of lithium ions with the carbonyl groups and strong intermolecular interaction between the lithium ion and the electron donor of PVDF. And also it is possible due to the formation of hydrogen bond between the hydrogen atom and phase carbonyl groups of NMP itself. So this infrared spectra show the change between the alpha conformation and beta conformations. And it will be nice if we continue to analyze these materials with the facility inframerah that's presented by Professor Pakorn. And this is the result of the harvesting of nanochloropsis. Here we can see the retentate color change at the end of the harvesting process at a virus addition of lithium chloride to the PVDF membranes. And this is the selectivity and the flux. The selectivity we call the percent rejections, and also the flux of the microalgae. Yeah, we can see the rejection percentage is achieved up to 100% here. And this is the color difference of microalgae retentate during the first 40 minutes of PVDF lithium chloride membranes. We see the different color degradation here. And then we see the water permeance at a various amount of lithium chloride addition to the PVDF membranes, and the SEM result between the PVDF itself and the PVDF with lithium chloride. And we also conducted the cleaning for the membranes after we use for the harvesting of nanochloroplast microalgae. We see here we use three kind of cleaning agents called citric acid and sodium hypochlorite, and also we combine between the sodium hypochlorite and citric acid here. And how to clean the membranes is just to immerse the membrane inside the solution. So we see after 5 cycles of the harvesting process, the membrane can be used with quite similar performance. It means that the membranes can be used several times by cleansing using the kind of solution. And this is the infrared spectra of PVDF lithium chloride membranes before harvesting and after harvesting, and also after cleaning with sodium hypochlorite, and also after cleaning with citric acid, and after cleaning with both natrium hypochlorite and citric acid. And then this is the mechanism of degradation at the membrane cleaning using the natrium hypochlorite and also the cleaning using citric acid. And thank you very much for your attention, and that's all for me. And I give a
All right, thank you, Ibu Nurul, for very wonderful lectures. Yeah, you introduced to us three, system, yeah, for your developed membrane. So firstly, you introduced the I call shortly 3M, yeah, mixed matrix membrane, which is really interesting. You try to combine the advantages for the polymeric membrane and also inorganic membrane, yeah, become the system. So in particular, the mixed matrix membrane preparations involve the polymer and also the filler, yeah, from inorganic material. And in case of its application for the separations, yeah, it exhibited a very interesting result. And secondly, also you introduced another system of composite membrane between PPF, yeah, and cellulose acetate for juice purifications. Yeah, it would be very, helpful, especially for food chemists, yeah, who would like to to clarify the water juice, the juice of apple. Me myself, preferable to have the clean one rather than the cloud one. And the third system also very interesting. Again, the the innovation in the composite between PVDF and lithium chloride, especially for harvesting microalgae. Then, yeah, it is really interesting. Yeah. Later on, maybe to the Q&A and discuss further. Thank you, Bu Nurul, for your good sharing.
welcome. Thank you.
Yeah. And finally, we come to the third guest speaker for our seminar today. Before Ibu Amanda start her presentations, I would like to briefly introduce Ibu Amanda. All right, so here is her following CV. Her name is Ibu Athanasia Amanda Septevani SD. I guess your birthday must be September, right? It's already passed. SD, and currently She's working in the Research Center for Chemistry, National Research and Innovations Agency-BRIN. Lately, still LIPI, or Indonesian Institute of Science, but currently it transformed, to become BRIN. And here is the following of her educational background. She obtained the sarjana teknik, from Universitas Diponegoro in major of chemical engineering, and then continues to her Ph.D. in the University of Queensland, Australia, in the major of maybe bioengineering and nanotechnology, especially. And also, he has the the profession academy as the profesi insinyur in Universitas Muslim Indonesia. Bu Amanda, very interesting of your educational background. And next, here is her related research work experiences. Really great to know she has a really great experiences. As the visiting researcher at several research institutions. From her CV, we can see that she has a great experiences as the visiting researcher in Oregon State University, United States, for the special project on atomic layer disposition of cellulose nanocrystal aerogel, and also as visiting academic of the University of Warwick, UK, for also the special project in publications of green bio-based cellulose nanocomposite polymer, and also another visiting researcher experiences in Politecnico of Torino, Italy. I guess this is this year, in the special project on publications of green 3D printed composite containing cellulose nanocrystal through digital light processing. Wow. Sounds really attractive. And she has great publications, even published around 13 patents. If all audience would like to further knows about our third speaker, also you can go to her Google Scholar or Scopus, even though maybe in the other connections, we can start to communicate with Ibu Amanda. I do believe she can share many great experiences. All right, Bu Amanda, without any further ado, I would like to give the time for you to start your presentation. So please.
Thank you very much, Ibu Fitri Korinisa, for the nice presentation, a nice introduction about me. It is such an honor for me to be here, to be invited by Universitas Pendidikan Indonesia and share our particular project to the audience here. And also it's such a great honor among the very great presenter here, Professor Pakorn and Dr. Nurul Widiastuti. I do hope that we can further collaborate our research, particularly, for example, for Professor Pakorn for giving us great advice, because sometimes we are lacking on further investigation of the certain characterization and fully understanding the mechanism of our material. Is such a great assistance if we can further collaborate with our institution, with Universitas of Thammasat. Also, Dr. Nurul, a very nice presentation. Thank you very much for sharing the presentation. And I do also believe that we can have a great collaboration, particularly for the application in membrane, because I believe that there is so much in further application that we can develop using our materials and your current existing research. So I would like to share my presentation. Okay. My current presentation will be focused on giving a broad overview of our research progress in our Research Center for Chemistry about the use of cellulose in the biopolymer composite. So I will divide my presentation into two categories. First is the cellulose. What is cellulose, the processes, the resources, and their characterization, as well as the use of the cellulose, particularly in polymer composite, and its application. So yeah, for the first outline, so cellulose is by far is the most abundant resources of biopolymer on Earth. And it can be derived not only from plant, for example, lignocellulosic plant, but also from non-plant, for example, bacteria, tunicate, algae. And if we can further isolate the cellulose from these resources of plant or non-plant, we can get the micro and nanocellulose that pose several advantages. So the first one is the high mechanical properties. As you can see from the table, that these when we can get the micro or nanocellulose, then we can substantially increase the properties of the mechanical properties. And of course, this is a good mechanical reinforcement for our polymer composite. And also for the, in case of the reactive surface, we can see from the chemical structure that there are many hydroxyl groups that it can benefit for the hydrogen bonding interaction, like Professor Pakorn explains before, that we can really then understand how much the hydroxyl group and how the mechanism between our cellulose with the polymer composite, for example. So when then we transform our cellulose into the nanocellulose, then we can get the very nice and transparent optical properties that sometimes is really great for our application, because it will not affect the color of the host polymer. And of course, it's biorenewable, biodegradable, and can bring the economical viable, because we usually derive our cellulose material from the local resources. So the isolation of the cellulose first from plant, for example, usually we use the biomass waste, because as we know, the biomass waste still brings some challenges for the environments. So if we can transform this biomass waste into the cellulose, then we can not only address the challenge in environment, but also we can add some value to the industry respectively. So first, usually the lignocellulose biomass, we treat it, chopping, grind it, and then we do the delignification. Mostly we use the natrium hydroxide, and then we do the bleaching. When after the bleaching, we usually can get the micro, or usually a pulp, or microfibrated cellulose. So if you can see from this figure, that the fibers is consist of hundred of microfibrils. Then, if we can then deconstruct that each individual microfibrils in accordance to the order or crystal domain or disorder domain, then we can get the cellulose nanocrystal with the high crystallinity, or the cellulose nanofiber, using several approaches. And also in terms of the after the lignification, during the process, we also can get the lignin-rich liquor, and then from this lignin-rich liquor, we can also derive to be several materials. But my presentation will be focused on the cellulose itself. So the cellulose content upon the processes, we can see from this table that, for example, we derive the cellulose from the oil palm empty fruit bunch and oil palm trunks. So comparing these two types of the resources, even though from the same plant, it will exhibit different characteristics of the cellulose. You can see even the composition of the cellulose, hemicellulose, and lignin is quite different, leading to different treatment of each material. So it means that different resources might give a different characteristic, and then we should try to find the optimum condition from each resources. So this is the morphology of the micro-size cellulose. For example, anti-fruit buns, raw material is pretty quite different compared to the palm oil trunks, when you can see distinctive microfibrils that attack on it. But then after the liquefaction, the morphology is quite similar. When you can see they are a microfibril that start to getting loose from the bigger bundles of fibrils. And then after the bleaching, we can get the totally individual microfibrillated cellulose, or usually we call microfibril cellulose, or MFC. So our Center for Chemistry has been successfully produced the large scale of microfiber cellulose in collaboration with the other institution, Institut Teknologi Indonesia, and also the company industry, PT Mandiri Palmira Arvindo. We successfully produced the cellulose with the capacity for the large scale is about 100 kilogram per day of biomass. And we also have a pilot scale about 1 kilogram day of biomass that we can also use to explore the others resources. So in this case, we use empty fruit buns for producing the microfibril cellulose, and we can get from our optimum condition, we can get about 70% of the cellulose. So once we can get the microfibril cellulose, then we can then do some modification further to get the nanocellulose. So there are several approaches to produce nanocellulose. First is the exit hydrolysis via the chemical approaches. So you can see this is the morphology of our cellulose after exit hydrolysis. From here, you can see that the root-like shape of the cellulose, nanocellulose, can be obtained from the strong exit hydrolysis, while for the mild exit hydrolysis, we can obtain a long entangle of the cellulose nanofibrils. So usually, by using the strong exit hydrolysis, we can produce a low aspect ratio. So the aspect ratio between the length and the diameter of the fibers is low when we using the strong exit hydrolysis. And while if we use mild exit hydrolysis, we can get the longer length of the fibrils with the aspect ratio medium to high. But interestingly, we also do some other resources such as corn cob. The corn cob, even though we're using the strong exit hydrolysis with the same condition, we can get the high aspect ratio, where the bleached corn cob usually they contain of the high hemicellulose that can influence the morphology of the nanocellulose after the hydrolysis. So in general, we can say that type of exit and then composition of the cellulose, as well as the biomass resources, is really play a big important roles to provide a different characteristic and morphology of the obtained nanocellulose. So this is the process to produce nanocellulose via mechanical treatment. So we use the homogenization up to 20K RPM. And from this, we can compare to the others experiments by using the mechanical approach that our approaches can produce nanocellulose without the impurity and the lower energy, which is very promising for the development of the nanocellulose at a large scale. So the other physical properties such as the crystallinity and the thermal stability by TGA, we can see that after the process of the production nanocellulose, we can get the crystallinity above 70. So the next one is the cellulose from the non-plant-based resources. So we call it as the bacteria cellulose. So bacteria cellulose we produce from the liquid waste of the tofu industry in Indonesia. So as we know that tofu play a dominant role in the economy because almost 84,000 tofu factories around in Indonesia, and they consume about 2.5 million tons of soybean every year. So there are two types of waste that produce from this type of industry, such as the solid waste. But from the solid waste, about 1 million tons, we can already have a good
utilization by producing the solid waste into, like, for example, the livestock fat, and then the fertilizer, and then the food product as well for human. Even one of them is my favorite. So the other resources of the waste from this industry are the liquid waste. In fact, this liquid waste is about 20 million meter cubic per year, containing a high BOD and COD. So even the color itself is also cloudy that influence the quality of water. And so intensive water treatment is really required to really utilize and use again the waste from the industry in terms of the liquid waste. In fact, this liquid waste is an alternative resources of a rich carbon and nitrogens. And from these rich resources, we can actually producing a cellulose from the bacteria secretion. So we have successfully produced the nata, the soya, and then transformed to the bacteria cellulose from this liquid waste tofu using the bacteria Acetobacter-Psyllium. And then after that, we do the deconstruction of the nanocellulose. So here is the morphology of the cellulose. From here, you can see that from the micro size, and then we can transform it to the nanocellulose. Interestingly, for the bacterial nanocellulose, generally is showing a longer aspect ratio than the plant-based nanocellulose. In terms of the crystallinity, it also have a higher crystallinity, perhaps due to the higher purity of the cellulose without any lignin and hemicellulose content inside the bacterial cellulose. So the next content will be the role of the cellulose in polymer composite. So both of the micro and nanocellulose is actually can be used as a filler and composite matrix. So as we know, the journal's idea about the composite is when we can combine and provide compatibility between the filler and the matrix. So after that, the filler itself is usually can be in the form of the particle or fibers, but the material that is impregnated or attached into the matrix usually can provide the benefit. For example, improving the mechanical properties. In terms of the matrix, then the component of the matrix that hold all the functional fillers together to form the bulk of the composite that later on can create a material which is specialized to do a certain job. So usually, once we obtaining the composite, of course, we can improve the performances, mostly higher mechanical properties. And also sometimes we can also introduce the biodegradability properties on our composite and surely a multifunction that can generate it after combining two or more material in our composite. In fact, micro and nanocellulose can play both roles as a filler or the matrix. So let's discuss first about the composite fillers. First is the use of microcellulose, our large-scale microcellulose. We already implemented in the in the food packaging. As we know that the current food packaging is mostly provided in the form of the styrofoam, which is sometimes can give a challenge in terms of the environments because it's very difficult to be degraded, and also some the health issue that may caused by these particular types of materials. So there are alternatives to give good properties as the food packaging, some like the starch-based biofoams. However, some research show that they are still pose low mechanical properties. So we thinking that maybe by modify and improve the mechanical properties can be done via reinforcing filler of our NFC. So here are the results. We can see that our starch-based biofoam with the MFC show extensively excellent mechanical properties with the higher mechanical properties up to 88% compared to the styrofoam itself. And when comparing to the neat starch biofoam without any filler, our microcellulose can enhance the mechanical properties up to 177%, which is really a great improvement. In terms of the biodegradable, it is also can be degraded in very short of time, within 5 days, by just burying our foams in the soils. But we still have some challenge. For example, when you see this morphology, that once we introduce our microfiber cellulose, there are big voids or this disturbed morphology that we will do some further improvement in terms of the dispersion technology, as well as inducing by the nanofillers itself. And we believe that this dispersion may further excel the performances of our biofoams. So the second one is the nanocellulose hydrogel. So hydrogel is a three-dimensional polymer matrix that is interesting because it can absorb a big portion of the water or other moisture, but without dissolving it. So recently that the hydrogel can also be applied in various biomedical applications such as diagnostics, preparation, tissue engineering, and drug delivery. So the characteristic of the hydrogel that should meet the biomedical application is first, the high absorption capacity with the minimum is 150 grams of water per gram product. And then of course the compatibility, because once we talking about the biomedical application, then we will talk about how we can introduce some biomarker or biomolecule on our systems. And the third one that is very important is the control release to the environmental stimuli. So the challenges still remain, for example, in terms of the low mechanical properties that can leading to the early release of the active ingredient. So we are thinking by introducing some nanocellulose, we can enhance the performances of the nanocellulose hydrogel for varied application in biomedicals. So this is the work produced by my master students for Wageningen University, Netherlands. So she successfully developed the smart wound dressing by introducing the nanocellulose from the bacteria nanocellulose into the alginate-based hydrogels. And as you can see from these figures, that when we haven't introduced yet the nanocellulose into the alginate system, the morphology of the alginate is still shrink and cannot be maintained a good stability after solid hydrogels form. So once we introduce our nanocellulose, interestingly that the nanocellulose can bring a good shape of integrity in our alginate nanocellulose. But then when we do some mechanical properties, we can see that significantly the nanocellulose inside the hydrogel can enhance the properties of the mechanical property compression test. And for the protein release, we can see that our nanocellulose can give more protein release in the hydrogel patch. So the second hydrogel nanocellulose produced by one of my master students, again, from the Andalas University, talking about the super absorbent of the starch reinforced with nanocellulose. You can see based on I took some important result from her thesis, that the absorption capacity by introducing our bacteria nanocellulose, it can significantly enhance up to 400 gram water per gram hydrogels. And it can also maintain the water retentions after several hours in a very high degree of temperatures. Which is this value of the high absorption capacity is really potential, not only for agriculture, but also even for drug delivery. So the third nanocellulose hydrogel that we are developing is in collaboration that currently I'm here to continue the collaboration that has been established since 2019. So this is my second visit, and we collaborate with the research group in Politecnico di Torino to develop the hydrogel using the digital light processing. So this digital light processing is basically photopolymerization when we put some photocurable polymerics on our hydrogel. Then by using using the GLP, it can give irradiating layer by layer of hydrogels to obtain a very complex and precise of 3D printed objects. So our previous visit showed that once we introduce the cellulose nanocrystal, in this case, when performing some mechanical properties by fully press of our hydrogel, we can see that without the CNC, the hydrogel can be easily ruptured. But for the hydrogel without the CNC, you can see that after fully compression test, it still can maintain the structure integrity, which is a really interesting how they bounce back after the compression test. So based on the storage modules, we can also see significantly that by introducing our nanocellulose, it can enhance the storage modules of the hydrogel. So the second one is talking about the nanocellulose role in the composite as a matrix. So the first one is we also do Dr. Nurul about the water remediation, but we really keen also to enhance our application in membrane. So our progress show that we know that the environment is getting worse because of a lot of activities like industry, transportation, residential, mines, agriculture even. And one of the proof of the deterioration of our environment is the Citarum River is pointed out as the most polluted river in the world. So our nanocellulose has been shown some promising results as the super absorbents, in this case as matrix. We already introduced two types of the materials. First is the activated carbons, and second is the magnetic nanoparticles. So in terms of the activated carbons, we can see that actually this nanocomposite is already show a good promise, such as give a really high efficiency to absorb the lead metals in water, in the contaminated waters. However, this cellulose composite only selective to the lead, while the other metals still have a low absorption efficiency. So then this year, we further investigate that by using another inorganic particles, nanoparticles such as magnetic nanoparticle, then we can use our nanocomposite to absorb various types of the metals in the multi-metal solution, which is very seldom to be done in our literatures, that it is very difficult and complex multi-function of the metals, and it shows a really great promise that can absorb even the arsenic up to 50%. So based on the result, we also can see that our cellulose not only can absorb the toxic metal ions, but also can degrade the organic pollutants, such as reducing up to 93% of the COD. So in terms of the reusability, we also do some testing, and we can see that after 3 times use of our polymer composite, it still can maintain the capability of the absorption towards metals. The second one is about the photocatalyst for the degradation. So we introduced the titanium oxide in our matrix of the cellulose, and it showed that it can degrade the dye. In the case, this one is a methylene orange up to more than 90%. And in terms of the rhodamine bay, because it's a less complex structure of the dye, it can really easily to degrade it even after less than 10 minutes. And in terms of the reusability, again, our composite can be used up to 3 times. So the second one is the nanocellulose as a matrix. This one is actually our long roadmap that can maybe we can further explore, that basically transparent cellulose nanopaper can also be obtained for the biomass in Indonesia. So paper, as we know, is mostly widely used as a material in our daily life, and at the nanoscales, as maybe you remember my previous slide, that it can provide the very transparent and good optical properties that in fact can be applied into various applications. For example, the LED display, supercapacitor, transistor, even flexible antenna and fuel cell. So comparing the cellulose nanopaper and conventional paper, as well as to the synthetic films like polyethylene terephthalate, we can see that cellulose nanopaper have a greatest advantage in the printability, that they, because of the hydrophilic characteristic of the nanopaper, they can easily introduce with the other functionals materials during the printability to further expand into the various applications. So we got some funding, and we can understanding how we can control the transparency while maintaining the mechanical properties. So in terms of the transparency, we can get more transparency of the cellulose nanopaper if we use nanocellulose derived from strong acid hydrolysis, which is usually have the morphology of the root shape, the very low aspect ratio. While for the mild acid, it will provide a very tough and stronger mechanical properties. So when we can combine two of these results, then we can get both the transparency as well as the flexibility. So I think this is the end of my presentation. I would like to sum up my presentation that you can already see that the micro and nanocellulose has been a great promise for various applications because it produces excellent properties as well as the results of the nanocellulose or microcellulose from the locals, which gives some cost-effective process. And I do hope also the multidisciplinary collaboration, for example, during the seminar, that can further expand the use of cellulose, micro or nano into various applications with the enhanced function. So to end this presentation, also I would like to thanks to the our research group, micromolecular chemistry group, with such a great solid team and cheerful environments, and also particularly for certain people that really closely help the development of the nanocellulose in the Research Center for Chemistry. Also would like to acknowledge the collaborator from national and also international to make it happen, the use of cellulose in the all of the life aspect as a material building blocks. Thank you very much for your kind attention.
All right. Thank you so much, Ibu Amanda, for very excellent presentations. You share many, great innovation, that been conducted in BRIN together with your collaborators. It's such, inspiring, for us how to improve many develop product based on cellulose, one of the huge abundant polymer that really abundantly available in our country. It's really inspiring. You demonstrated to us many plausible application that can be done one time. The cellulose derived from the macro structures to the nanostructures, even though it can contribute many excellent properties, not only how to strengthen the mechanical properties of the system, but as well other properties. The last one, really really interesting about the transparent cellulose nanopaper. I guess the participant also would like to us to discuss further with all of you. So now I guess I don't need to summary since Bu Amanda also already deliver the presentation very clearly. And to all my beloved participants, now we come to the Q&A sessions. We can start from the questions that been written here in the chat box. First question, I guess, is delivered to Prof. Pakorn from Adam Nugraha. Dear Prof. Pakorn, what strategy that possible to do if we want to conduct the TIR or Raman analysis for 1D, 2D, or 3D crystal geometry? Assume that the structures give recognizable difference based on hydrogen or OH bonding and statistic determinant. Thank you in advance. So please, Prof. Pakorn.
Thank you very much. That is very good questions. Yes, to study structure, right, especially in that have directional orientation, like different directional orientations, we can use normal FTIR, like either in ATR or transmission mode, but using a polarizer, so we can measure vibration in specific orientation, right? A different angle, at least at 0-degree angle and 90-degree angle, or we can vary the angle up to any other angles rather than this as well. And once we get that information, we can at least identify the isotropic property or anisotropic properties of the crystal structure, right? Or if we want to look at the formation mechanism, we may also use heating cell, right, to heat or to melt the structure, and then we record spectrum of the sample as a function of time, for example, and we can then get some information about what happened to the functional groups, specific functional groups, and in terms of kinetics. And also, if we have like a series of spectra as a function of time of crystallization or time of melting of the crystal, we can use that to generate 2D correlation spectra of the sample, right? Which is the topic that I haven't gone through for today, right? Maybe in the future time, I may give a presentation on that specific topic later. So by using that technique, right, we can look at sequential change. We can look at what functional group, right, change first during the crystal formation, for example, and which functional group change after that functional group or change at the same time. So by having this sequential change information, we can then discuss the mechanism in terms of interaction between functional groups, right? Or the induction period or the crystal growth period, right? Something like that. Yeah, I think this can be applied, right, to this system and give the information that the from Dr. Adam. Yes. Yeah. Yeah. I hope that this answers your question. Yes. Yeah. And we have all of this accessory in our lab, right? If you would like to do the measurement, right? But if you have access to those accessory, right? So some of these accessory are quite unique, right? Not every lab may have, right? So, but they are possible by this technique.
Yeah, by applying special accessories. Yeah. Hopefully, right. Maybe yes. In the fourth seminar, you can continue your presentations regarding to the 2D or 3D.
Right. Yes. Maybe we may change the topic a little bit. Yes.
Yeah. Yeah. It's quite new, I guess, from Indonesian scientists. Yeah. To do with that typical analysis. All right, Adam, hopefully it answers your questions. If you still have any additional question, you can raise your hand, or even though you can write down again your question in the chat box. All right. And then let's continue to the second question from Hari. Yeah, this question for Ibu Nurul. Dear Ibu Nurul, is there any impact on immersing the membrane for too long time, maybe, yeah, in the coagulation bath? How do we know if the EMTS process has been completed, done? Yeah, thank you so much.
Okay. Hello. Thank you. For the questions, Mr. Hari, what the impact on immersion? Yeah, immersion of the membranes for too long in coagulation path. The function in ion phase process in coagulation paths is to release the solvent that we use when we are preparing the materials. Yeah, when we are preparing the materials. So when we immerse the polymer solutions inside the coagulation path, so that will be the change position between the solvent that's released into the coagulation path, and also the non-solvent, they call non-solvent, replace the release of the solvent, so they become membranes, solid polymer solid. So what the impact is actually is not the big impact, even we immerse in the long time, yeah, when we are immersed the coagulation paths. But normally and better if we merge the membranes in the coagulation path and using water and it's not immersed but also rinse the water several times, so it will make sure to release the solvent, yeah, the solvent. And if we several times is enough to get that condition, I think.
Yeah, I guess it answer your question, Hari. Again, if you still have any additional comment or question, you can write down or raise your hand, yeah. And then another question, still to Ibu Nurul from another Adam. This is Adam Jaya, previously Adam Nugraha.
Okay.
Dear Bu Nurul, if it's possible to convert the membrane into film type membrane, for example, to HO, yeah, several type of gases to prevent it penetrating to the surface of the substrate.
Okay, absolutely, it is possible if we want to convert the membrane into the film type of membranes. Yeah, several types of gas will pass through the membrane or the film, so that's very possible to prepare the materials like that, and for the application as well.
Depend on the target application, maybe, yeah, Bu Nurul?
Sure, yeah. Depend on the target of the application. So as a principle, that's absolutely possible.
Yeah.
To use that.
Right. And then the next question from ITE Ibu Anik, I guess. This question is for Ibu Manda. Dear Bu Manda, I want to ask about the nanocellulose processing. Is to 20,000 RPM of the optimum speed of the homogenizer that you apply, maybe, yeah? And how about the durations of using homogenizer?
Thank you very much for the question. So actually, Buan is one of my collaborators in my particular research. So yeah, it actually depends on the resources again, because the maximum that usually we apply to our process is 20K RPM. Because above that 20K RPM, sometimes the machine cannot hold on. So it will be difficult and challenging if we push further up above the 20K RPMs. So we can then play, it is right, the duration of the process. But please be careful. So you can do variation and optimization based on your resources. But please be careful, especially that because cellulose sometimes easily to degraded into the glucose, because cellulose is particularly is two anhydrous glucose that standing together. So please be careful
that your cellulose can further degrade to the glucose because it will turns to black. So in order to avoid that issue, you can apply some ice isolation put it in your chamber to make sure that temperature it maintains in the low temperatures, perhaps about 10 degrees Celsius or to 0 degrees Celsius, and to make sure that your cells is not degraded. And then you can analyze based on the morphology, XRD, and so on. So I cannot say the duration exactly because it really depends on the resources itself.
So it's mean the sonications condition also still can be optimized, yeah?
Yeah, we use the homogenization that's particularly quite different with the sonication. So
I see.
homogenization, that the mechanism is your materials is absorbed into one nozzle, a small nozzle, and then dispersed in very high speed of RPMs. While for the sonication, usually there's a strong intensity of the machine that attack your material. So in our case, we use the homogenization.
But the principle may be still mechanical treatment,
yeah. So the mechanical treatment can be applied into various methods. One of the homogenization. You can also actually use the ultrasonication. Yeah,
very interesting, Bu Manda. New knowledge as well for me myself. And next, we still have question here in the chat book for Pakorn. So dear Pakorn, what and why is the difference when the sample measure at 0 and 90 degree regarding to the direction of the light scattered in ITR, FTIR?
Okay. So actually, when we apply polarizer with FTIR measurements, it is common for using in transmission mode. So we shine it infrared light through the sample, right? But before that, we use polarizer to only filter out a certain plane of light. And then, so when we measure at 0 degree and 90 degree, this can provide the two extreme of orientation for us, right? So if we measure at the same spot, at 0 and 90 degree, if the spectra, right, have no difference between these two directions, it may mean that our sample is isotropic, right? So no orientation of the structure. But if we see different in the spectra, right, at 0 and 90 degree, now we know that there are some specific orientation of the crystal structure or certain functional group in the sample, right? So if we know this, we can then go further into the detail, right? So that is the importance of using polarizer in the measurements.
All right. So hopefully it answer your question. Yeah, if you still have any additional questions, you still can continue, yeah, in the chat box. And some questions come to my WhatsApp. I'm not. I can read for all of the speaker here. So post question to Ibu Amanda. So there is the wetting phenomenon in the conventional paper. Yeah, is it also can be happen in the nano paper? For example, if the liquid drop on the paper, yeah. Maybe the question is she would like to know about the surface nature, yeah, of cellulose nano paper that you produce.
Pardon me, I can't hear clearly. Is that wetting?
Wetting.
Okay.
Yes.
Wetting.
Yes.
So it
Wetting phenomenon.
Yes.
Yes.
Wetting
Yes.
phenomenon.
Yes. That's right.
Yeah. When we talk about the paper, general paper, including the nano paper, it is hydrophilic. So the hydrophilicity or the wetting test is usually will show some high hydrophilicity. So it is somehow give some benefits, in some point also give some challenge. Because first, in terms of the benefit, I can say that you can easily functionalize with the other inorganic materials. For example, if we want to apply as the supercapacitor or other like fuel cell, when you want to put some materials on it as a function of that application, you can easily functionalize through the hydrogen bonding or some chemical interaction. But then it is also give a challenge because of the hydrophilicity, it can easily absorb the moisture. So in that case, once you are doing some functionalization, you should make some modification again on the surface characteristic to turn it into the into the hydrophobic characters. So yeah, there are some process that we are doing to go to that application, but yeah, it comprise of a quite complex procedure. But you can message me an email. In my slide also I put my email, then we can further discuss how we can modify and the surface modification of the cellulose nanopaper.
All right. I guess it answers your question, yeah. And also the question to Prof. Pakorn, how do we conduct the quantitative analysis using ATR mode when the peak on the low frequency tend to be sharper, but in the higher frequency the peak is weaker?
Okay. Yes, thank you. Actually, ATR can be very easy to do quantitative analysis because the path length is fixed. Right? If you do transmission mode, the path length means the thickness of the sample. Right? It is very hard to control the sample to have the same thickness. Right? However, if you use ATR, right, the depth of penetration, right, is fixed if you use the same crystal and same type of sample. Therefore, this is very convenient for doing quantitative analysis. However, now, if you worry about the depth of penetration at different frequency, this will happen, right, to all sample the same way, right? Therefore, if across sample you use a certain band as a reference and you normalize your whole spectra by the reference band, right? You can compare other band, right, across sample conveniently, right? So I can say that ATR can be a very, very common technique for doing quantitative analysis, especially if we compare similar sample. Right? It may be hard to compare different sample, right? But if we do quantitative analysis, we need to do standard curve, right, that are made from same type of materials, right? So ATR is the ideal solution.
And the additional question is, can you suggest the software to obtain the better information for from the spectra that we have? For example, maybe the student already have the FTIR spectra, and then how to do the processing, maybe, Prof, with the spectra to get more clear analysis or something.
Okay. The common program, right, software should be the software that comes with the spectrometer. For example, Bruker or thermonickelette, like Omnic software. But there are some shareware or free software that are quite good as well. One software that I would recommend you may want to look at is called SpectraGrip. SpectraGrip. This is free software that you can search from the internet. Yeah, let me look. SPECTRA. And what? GRYPH.
DRYPH.
Yeah,
Yeah.
Spectra Grip. This
Yeah.
is a very good software, and it is available for free for educational use. You can contact the developer, and he will send the key for the software.
I see. I see. I see. Yeah, I guess all participants, you need to note the software name. Yeah, after this conference, you can quickly search. Yeah, because the software is free and hopefully can support you to get the better analysis result. Yeah, on FTIR data.
Yes.
And still other question to my WhatsApp for Ibu Amanda. What is the problem that could be occur when we employ nanocellulose as a metric in photocatalysis applications?
What is the problems?
Yeah, maybe the shortcoming or the obstacle, maybe, or something like that. The meaning.
Yeah. In terms of the performances, we can see that our nanocellulose composite already show some good promise to degrade the dye components. But as I explained previously, it is a challenge because when we conduct cellulose and apply it in waters, there will be some challenge when we want to separate it, particularly in the large scale. In the case of the superabsorbent, if you still remember my slide, that we also apply with the magnetic nanoparticle that can help us to separate it, our composite once the process finishes. But for the photocatalytics, we still only combine between the nanocellulose and titanium oxide modification. So we still haven't applied some techniques that can help us to separate our composite with the treated water. So that is still our homework. So yeah, we need to do some further modification in order to easily separate our composite in the treated water. That's really great question.
All right. Thank you, Ibu Amanda. Hopefully it answers your question, yeah, for the participant who joined with us through YouTube, I guess. And another question to Ibu Nurul. So today, so many questions, yeah, very interesting talks that just delivered by our three speakers. For Bu Nurul, you introduced the composite system between zeolite template carbon and polysulfone, right? And then in the result, it demonstrated that the addition of polysulfone into GTC improved its selectivity. So what was the mechanism occurred on this process? Still mute, Bu Nurul?
Okay. Sorry. Thank you very much for the great questions. And in our membranes, where we use a zeolite templated carbon as a filler in a mixed matrix membrane based on polysulfone, the functions of zeolite templated carbon is selected materials that can design the pore size of the carbon, that will have significant impact on the selectivity when we use that for gas selection. Yeah, when we use for gas selection compared to activated carbon, if we use the activated carbon, because the zeolite templated carbon, the structures is more homogeneous, the pores is more homogeneous, and they lack negative structure of the zeolite. So the zeolite templated carbon have two properties combination between the zeolite and carbon itself. And with the carbon itself, we know that the high surface area of the zeolite templated carbon is much higher compared to activated carbon, or even the zeolite itself when we use the zeolite as a filler. Yeah, and the properties of the carbon itself, they can reduce the void that can appear due to the void due to the interface of the filler and with the matrix of the membrane. So that is the benefit of using cellulose templated carbon in this case.
All right. I guess it answered, yeah, the question from the participant on YouTube. And then another question to Prof. Pakorn. Since you, how to say, demonstrated that the FTIR can be applicable for a structured elucidation, is it possible to elucidate the R or S confirmation, yeah, structure, or using FTIR? Like maybe
No,
optical
unfortunately,
confirmation? Cannot, yeah?
FTIR cannot
Mm-hmm.
the configuration.
For the R and S, yeah?
No, cannot. But if the R and S configuration, right, influence other different in the bigger structure, we may be able to obtain some information on that. But it cannot be directly used to determine R and S configuration.
Is it necessary to apply the special accessory to come to that result for confirmation?
Uh, no, with no. What I know of is we cannot do because FTIR detect the absorption of infrared light because of chain vibration, and chain vibration here is not specific to direction of the bond, right, around an atom. However, for example, the example that I give on a stereo complex structure of polylactide, right? That is a result from R and S configuration of repeat unit of lactide, right? But make the big crystal structure different. FTIR can provide information on the big stereo complex structure, which is the result from RS configuration. Right? But it cannot be used to directly determine R and S configuration.
I see. I see. And one additional question to Prof. Pakorn from Raman spectroscopy. Since we can apply different type of laser sources, so is there any difference in terms of Raman spectra that can be obtained by using different lasers?
Right. Very good question. Because when we use laser, right, to shine on the sample, many things can happen, right, especially fluorescence, and therefore we need to choose appropriate wavelength of laser for specific sample in order to minimize fluorescence signal and also enhance the Raman signal. Right? And we may need to, there is some rough guideline for which laser we should use for which type of sample. Yes.
All right. All right. Hopefully it answers, yeah, the questions. And the last question to Ibu Manda regarding to the nano paper that you just presented on the last presentation. You demonstrated the great properties, yeah, of nano paper in terms of optical properties. How about the electrical properties?
Yeah.
Did you check, maybe did you have any data regarding to the electrical properties of your nano paper, so it can meet for some applications, maybe
Actually we already did some experiments to introduce such as the B.PSS as conductive materials and do some conductivity performances in order to see whether it can be applied to the electronic properties. But I haven't shown in my slide because the process is not completed yet. So basically, once we introduce the
conductive materials into our cells on the paper, then we can get some results on the conductivity value that it can be applied for the processes such as applications such as LED, or even we already do some modification in terms of the fuel cell to apply some dye synthesis of the conductive materials onto the material, but it's also haven't completed yet. So yeah, maybe in the next
seminar,
session, yeah, I can update all of the experiments that we are still progressing to do.
Yeah, very glad to know. Yeah, still many work in progress. So later on we can have another seminar. Yeah, to hear from Ibu Amanda for the progress.
I have one question for Dr. Amanda.
Please, Prof. Pakorn.
Yes, thank you. When you show us the application of your cellulose material with surface modified by nanoparticles, right? When you apply this to water treatment, right? What form of your product you apply? Right? I see that you draw a sheet structure.
Yes, actually we can use several forms depending on how we process it. For example, if we use the ultrafiltration, for example, because we need to do ultrafiltration because our material is in the nanoscales, then we can get some like a thin film layer. But then we also can do some freeze dry, and then we can get some powdery form. So
yeah,
it is also interesting to share actually that depending on the shape form, because it will also create some different surface access or the surface ability to absorb some like contaminated water. So it will also give some effect that also very interesting to be further investigated, Professor Pakorn. But yeah, we are still long way to really understand and investigate every single application. So I do really hope as well to really collaborate, for example, with Dr. Nurul in terms of the membrane, and with Professor Pakorn in terms of the understanding the mechanism and everything that we are still lacking on it. I should admit it.
Thank you.
Thank you very much for the question.
Thank you, Prof. Pakorn. Thank you, Bu Manda. And just one question come to my WhatsApp for Ibu Nurul. Dear Ibu Nurul, how to overcome the falling that would be occur on the system for apple juice filtration? Yeah, that's the question.
How to overcome? Would you please repeat?
The falling.
The falling. Oh, all right. The falling. Yes. The big challenge in membranes, especially for ultrafiltration membranes, is the fouling. Yes. For apple juice clarification, we haven't tried to clean up the membranes after fouling. But for microalgae harvesting, we already conducted the research on the how to clean the membranes after the fouling with the microalgae. I think that's same thing. We can use several types of cleaning the membranes using chemical cleaning, such as exit or exit types, or other chemicals that we can use for cleaning. But that is that we consider is first is the chemical for the cleanings should not destruct the structures of the membranes itself at a certain amount and concentration as well. And we have to try the cleaning first at the same time, and then continue how many cycle, how many cycle that we can clean the membranes, for example, by see the reduction of the performance of the membranes after cleaning, like what we already conducted for the cleaning for the microalgae, we found that at several times, such as 5 times cleaning cycle, the membranes can still have quite similar the performance. Thank you.
By applying some, how to say, cleaning or washing process, yeah?
Yes.
By means of some chemical, but of course, we have to consider the nature of the chemical.
Sure.
Yeah.
Yeah. Other methods is also possible using physical cleaning. Physical cleaning like using air flushing. Air flushing. Yeah. Backwash. Yeah. That is also possible. It's really depend on what we are using of the techniques. Yes.
So besides the chemical treatment, the physical treatment also.
Physical treatment is also possible. Yes. Air flushing is also possible. Yeah.
All right. So, dear participant, if you still have any question, we still give you the opportunity for 1 or 2 short questions, please. Even you can open your microphone, yeah, and then raise your hand to directly interact with our speaker. Or it's clear enough? Yeah, time flies so fast, almost 3 hours. We stand here, but really great. Yeah, we have many excellent interactions in the Q&A. So many questions come. So if there is no other questions for closing this seminar, I would like to give the last opportunity to each invited speaker to deliver your closing statement. Please, maybe it can be started from Prof. Pakorn and then continue to Ibu Nurul and then Ibu Amanda. So please, Prof.
So first of all, I'd like to thank Professor Fitri for organizing this wonderful lecture today again, and also Dr. Amanda and also Dr. Nurul with a very interesting presentation along with our lecture for today. And also today, all questions from the audience, they are very so many interesting questions and very lively to have a good discussion like this. And yeah, and we still have one more lecture
right.
in this series.
Yeah.
So hopefully you are able to join us for the next one as well. And yes, thank you very much.
Thank you so much, Prof. Pakorn. And then next, Ibu Nurul.
Okay. Thank you very much for the great seminar series here. We can share our results, and hopefully in the future we can collaborate. Professor Pakorn and also Dr. Amanda and also Dr. Fitri and all of the participants who attended this seminar. We also possible to have a collaboration together that may be interesting for us to do research together in the future. So this is thank you very much once again, and see you for the next seminar or the next collaboration with us. Thank you.
Terima kasih Ibu Nurul. Thank you so much. And last, the last, Ibu Amanda, please.
Okay, once again, yeah, I should say very thank you for inviting me to be joined in such a great event, because from the speaker, not only the audience, I also can learn how great potential on the FTIR actually that we can further develop, as well as the further update on the membrane technology from Dr. Nurul. It's such a great opportunity for me to join, learn, and discuss together about the progress. And I can't wait for the further collaboration between us, between Universitas Pendidikan Indonesia, ITS, as well as with Professor Pakorn. Thank you very much once again.
Thank you so much, Mumanda. And yeah, we do hope so. Yeah, let's we make it real next year after Mumanda return from Italy. And yeah, to close this session, on behalf of the chemistry department, I would like to deliver our Sincere gratitude for all of your excellent and wonderful contributions, especially from our invited speakers. So firstly, here is the e-certificate for Associate Professor Pakorn Opaprakasit. Thank you so much, Prof, for your continuous and great support to our program, and especially for today presentations. Yeah, very wonderful, very excellent. Yeah, and secondly, also we would like to deliver our gratitude to Ibu Nurul Widiastuti, Ph.D. Here is the e-certificate, yeah, as the invited speaker on this third seminar. Thank you so much, Bu Nurul, for very insightful talk today, and then you bring us
Thank
to
you.
the real application, yeah, from the polymer composite system, especially in the membrane application. Thank you, Bu Nurul. And the last
Thank
but
you.
not the least, yeah, here is the e-certificate for Ibu Athanasia Amanda Septevani. Thank you again, Ibu Amanda, even though you are away, you are away from the country, but you still provide the great time to join with us to share many, how to say, great innovation on your current work. Yeah, and hopefully later on we still can hear, yeah, from you about the progress. And yeah, very looking forward for the future collaboration with all of you. And yeah, thank you so much. And before we close this session, maybe we can take the photo session together with our beloved invited speakers. So to all participants, please kindly open your video. I deeply understood for the long time meeting, sometimes we have to save the internet connection. So the way how to save is just turn off the video, yeah? Yeah, it would be very great for us to have the photo session together. And after this, the committee will share the attendance link, yeah, and soon after you fulfill the attendance link, we will send the certificate, yeah, to all of your email address. All right, Bu Amel or Bu Mita, could you please support us to take the picture? All right, you can put any kind of style. Yeah, it's really the special time. We can have the frame together with Prof. Pakorn, Ibu Nurul, and Ibu Amanda. All right, so maybe I can help to counting. Okay, everyone, please be ready. All right, 3, 2, 1. All right, and the second layer, I'm not sure which layer you are existed. And then 1, 2, 3. All right, and the third layer, 1, 2, 3. All right. Thank you so much, everyone. Thank you so much again for your great availability to attend our seminar, and please kindly refer to the chat box. We provide the link to fulfill your attendance for this third seminar. And again, gratefully thank you to our speakers for your excellent, wonderful, and very, how to say, fruitful discussion, yeah, that been delivered in our third seminar. Again, on behalf of the chemistry department, as well as the committee of the World Class Professor Program Scheme B for this year, yeah, we do sincerely thanks for your great availability and also great contribution on our seminar. I do hope all of you stay healthy, yeah, and yeah, very looking forward to see you again very soon in better situations. And just for your information, here is the last seminar that we would present on the podcast professor program. In the last, how to say, slide delivered by Ibu Amanda, here there is one, the collaborator, Prof. Basuki Wirjo Sentono from USU. Yeah, he will be our invited speaker for the last seminar, as well as one of the colleges of Ibu Amanda, Prof. Subiakto from Research Center of Biomaterials, BRIN, and also Pak Nasir, yeah, from LPTB BRIN in Bandung. Yeah, again, I sincerely invite Bu Nurul and Bu Amanda, if you still have a great availability, to join again with us and to see again with Prof. Pakorn in our fourth seminar. All right, everyone, thank you so much. Stay healthy, stay happy, and see you again in the next seminar. Thank you so much.
See you.
Thank
Thank
you.
you.
Terima kasih banyak Ibu Amanda, Ibu Nurul, Prof. Pakorn.
Sama-sama, terima
Sehat
kasih.
selalu,
Bu.
sukses
Ya,
untuk
terima
proyeknya
kasih.
Bu Manda.
Iya, siap.
Amin.
Pasti
Bu
kita
Nurul
update
sehat
dan
selalu.
kontak. Ya, terima kasih.
Ya, terima kasih Bu. Amin,
Terima
sehat
kasih,
selalu
Bu.
semuanya.
Terima
Sukses
kasih.
Bapak Ibu.
Ya, terima kasih. All right, to all participants, so please kindly fulfill the attendance link that just provided by the committee on the screen. Yeah, it would be very helpful for us to receive your information. Then we can quickly proceed the e-certificate that can be delivered to your email account. Yeah, and again, I would like to thank for all of your great attention and also your great attendance through this third seminar, and very looking forward to see you again on the last seminar, yeah, that organized by Wood Class Professor Program by Chemistry Department, Indonesia University of Education. And I do apologize if there is any, how to say, inconvenience during, how to say, hosting this lecture or this seminar. And yeah, really looking forward to see you again on the 22nd, yeah, of October for our last seminar. So we will send the flyer immediately in our how to say, social media of our department, and yeah, kindly grab for your registrations. Yeah, looking forward to see you all again, and selamat sore, selamat beristirahat, terima kasih banyak. Ibu Nurul, terima kasih banyak. Semoga sehat dan sukses
Terima
selalu.
kasih Bu,
Semoga kita
sukses
bisa
selalu Bu Fitri.
berkolaborasi secepatnya Bu.
Insya Allah
Terima kasih.
nanti kita ketemu lagi.
Ya,
Terima kasih banyak Bu.
Yeah, baik. And finally, I would like to close the seminar. And thank you so much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.